So good morning everyone. Today we will start with the second chapter in fact. So herein we will be talking about the different transforms that are being used in digital signal processing and also the biomedical signal processing. Okay. Um so the first transform it is Fourier series, second is Fourier transform, then third is discrete time Fourier series, fourth is discrete time Fourier transform, fifth is discrete Fourier transform, then sixth is Laplace transform, and seventh is Z transform. The first two transforms they are meant for continuous time signals. So we can analyze the continuous time signals and the systems using the Fourier series and the Fourier transforms. Okay. Then we have three transforms, uh, namely the discrete time Fourier series, discrete time Fourier transform, and discrete Fourier transform. They are meant for discrete time signals. Okay. So among these three transforms, the most utility is for the discrete Fourier transform. We will see why this is so. Because if you see in our practical this applications, we hardly used discrete time analog signals. Why? Why? The reason being, whatever the analog to digital converters are there, or the digital processors are there, they are capable to handle minus 5 to 5 volts, or minus 10 to 10 volts, or even if you get a very good thing, you may go for minus 20 volts to plus 20 volts. So that is the limit. However, as I told you previously, in the continuous time analog signals, uh, the amplitude values, it can have any number of values, and its amplitude can also the delta x or the delta y in the of the, that means the difference between the two amplitude levels, it can be as small as possible, that is, it might be tending to nearly equal to zero. Okay. Also, its amplitude values can be ranging from minus infinity to infinity. But if you see, all the digital systems or the digital processors, they are not able to handle those kind of things. Okay. Also, you must have seen while you are using the computer, if your computer becomes slow, so what do you do? The first thing you do is the clear the cache. Okay. Why? Because you think that majority of the memory of the RAM, random access memory, it is being used by the temporary files. So what does that mean? That means there is a limit on how much processing your processor can do. Okay, so there is a limit on that. So if there is a limit, you cannot handle infinite number of processors, okay, simultaneously. We will see why I am telling that we need an infinite number of processors to be computed while doing some what you call while doing some yeah, what you call calculation or processing of the signals. Okay, so to eliminate that, we have this discrete Fourier transform. Okay, the properties of the discrete time discrete Fourier transform, it helps us to manage digital signals. Okay, to manage digital signals. So it is compatible with our digital signal processing. Okay, so you can handle whatever the signal is given to you under the practical considerations. Then next is Laplace transform. So it is mainly used for the development of the systems, and to a certain extent analysis of the signals also. And lastly, Z transform. It is basically used for developing digital systems. Okay, so in our class I will be giving you just an overview of from Fourier series to discrete time Fourier transform. Okay, then we will be discussing this discrete Fourier transform in detail. We will see how it is able to handle the signals, and then we will also be discussing the Z transform in somewhat details, so that we are able to design filters. Okay, so we will not go into very much in depth for the Z transform, but we will gain the knowledge so that we are comfortable in designing the digital filters. क्या हुआ, बहुत मुस्कुरा रहे हो? बहुत मुस्कुरा रहे हो? हाँ. Anyway, so another important thing is that this Laplace transform, this is an extension of the Fourier transform. Okay, it is a more generalized version of the Fourier transform, and due to this reason, it is able to handle we can use this transform to analyze this marginally stable systems also, in comparison to the Fourier transform, which is restricted in a particular domain in the uh, complex plane. Okay, so देखो तो कौन है, उसको खोल के रख दो तुम. हाँ हाँ, कम कम. Okay, so what is Fourier series? So Fourier series, it is nothing but it is a series which is meant to represent a periodic signal. Okay, so we have all discussed what is a periodic signals. Periodic signals is a signal which follows the this equation x t equals to x of t plus capital T for all t, where this capital T is nothing but the fundamental period which is related to the fundamental frequency using this formula. Capital T equals to 2 pi by omega naught. Okay, so when we say this, there are two basic periodic signals. First one is the sinusoidal signal. It may be cos of omega naught t or sine of omega naught t. We consider both as the sinusoidal signals. Why sinusoidal? Because if you do some phase shift in the sine waves, we can get the cos wave. Okay, so that is the major reason why we call it just sinusoidal reason and not sinusoidal reason signal or something like that. Okay, so sine wave was the basic signal which was invented first, and this cos signal can be derived from the sine waves. Due to this reason, we tell that any signal which is oscillating at a particular frequency, that they are sinusoidal signals. Okay. The second thing is the complex exponential. Now, when we talk about this complex exponential, which is given by xt equals to e to the power j omega naught t, so we can represent this in the form of e to the power j theta, which can be written as cos theta plus j sin theta. So here also, if you see, it is a complex addition of sinusoidal signals, and they are also basically periodic in nature. So complex exponentials, they are also regarded as the periodic signals. Okay. So what does the Fourier series says? This equation over here represents the Fourier series. So what is it? It says a signal xt, it is a linear combination of complex exponential signals which are given over here. I told you this e to the power j k omega naught t, it is a periodic fundamental periodic signal. So if you see complex exponential signal, it is a periodic signal, right? So what is AK? AK is nothing but some constants. It is a constant multiplier. Herein, this k value, it changes from minus infinity to infinity. Okay. So when k is 0, this component, it becomes 1, right? And we get AK, which is basically a constant. So what is this constant? Suppose you are analyzing any signal. We have a sinusoid signal like this. Okay. Now, in some cases, you may find the sinusoidal signal has shifted up. So what has happened? There is a DC shift in the signal component. So this DC shift, what is this DC shift? It is a constant value which is being added to each of these signal component of the sinusoidal waves, right? So this DC shift, it is basically the AK or the constant when the value of k is 0. Okay. Then secondly, if you place k equals to 1, so fundamental frequency or the first harmonic component, and the A1, it would be the DC shift associated with the this fundamental frequency or the first harmonic component. Okay, it may be 1. If it is 1, that means 1 multiplied by something, there is no DC shift. If it is 2, then there is some shift. If it is zero point 0.5, again there will be some shift. Okay. Then in the second one, k equals to plus minus second harmonic components. Sorry, no, yeah, not the DC shift, the amplification. When k equals to plus minus 1 root and nth, these are basically amplification. So sinusoid amplitude, it will be varied. Okay. So the first one is for the DC component or the baseline shift. Then in the second harmonic components, again your amplitude level of the sinusoid signal, which is constituting the periodic signal, it may change. And likewise, you can go for the nth harmonic components, because uh, this, as we told you, that it can go from minus infinity to infinity, but practically it is not possible. So we go to we trade off somewhere, and we find out that what is the minimal value of the k, which can be used to represent a periodic signal uh, in a pretty clear manner, so that uh, whatever information we want to convey to the other side, so we are able to convey them. So these are all the derivations. I am not going into that thing, but the finally, uh, what is the output in the complex plane? We have this xt equals to a0, which is the DC component, and then we are having cos and sine components. So from here we can see that we will be having a DC component, and apart from that we will be having complex sinusoids, which will be representing our periodic signal. Okay, so this is the gist of the Fourier series. Fourier series means any periodic signal, they can be represented with a series of sinusoids. So this is a pulse wave. So you can see initially, if you see, the first harmonic is used, then another component it has been added, then another component has been added. So if you see, as we go from B to D, we are getting to a position where this solid line, it is tending to the our original curve. Okay, but it is still not the same. However, when we have increased the k value, okay, or you can say we have gone up to the nth harmonic, we are getting a solid line which is nearly representing the original curve what or the original pulse graph what we have seen. Now in this case, if you see where there is not much change in the what you call voltage levels, whether it is the Bessel level or it is the maximum level. If you see, there are some ripples, but these ripples are not great. Okay. However, add the discontinuities, add the discontinuities, you will find that the approximation is not that clear and there is a shoot up or shoot down. Okay. So this phenomena is regarded as Gibbs phenomenon. This phenomena it is regarded as Gibbs phenomenon. Okay. So why this is happening? This is happening because if you consider any of the equation, whether you consider this equation or you consider the first equation over here, what we discussed, we told that we will be synthesizing the periodic signals using infinite number of sinusoids. Okay. However, herein we are restricting ourselves to the nth harmonic component. Okay. Now, due to this reason, since we are restricting it, we are getting a signal which is as close to the original signal, but since we are not able to use infinite number of the sinusoids, there would be some deviations, and those deviations are being uh, accounted for through this uh, Gibbs phenomenon, where there is a overshooting of the amplitude levels. Okay. Now again, if you see the triangular wave, so this triangular wave, it will have a fundamental frequency. Then you can have this second harmonic, third harmonic, and also if you see over here, the phases in all these things, they are uh, they are what do you call it? It is similar to the what do you call it? It is similar to the fundamental frequency. If you see over here, it starts from the origin wherever you want, it is starting from the origin, and then the frequency component it is variable. Then coming to the Fourier transform, from this slide, can you tell me what is the gist from here? The first thing, you should look into this equation. Can you recognize this equation? Mm-hmm. Yeah. So in the Fourier series also we have started with this equation. Okay. So in Fourier series we talked that the analysis, the Fourier series can only do the analysis of the periodic signals, but Fourier transform is for, it is only for non-periodic signals. How many of them of you can tell me whether it is also for the periodic signals or not? No. Hmm? Anyone else? कितने लोग बोल रहे हैं पीरियडिक एंड अपीरियडिक बोथ? Only for, rest of you are telling that it is only for aperiodic. So those who are telling that it is for aperiodic year, so that is incorrect. It is both for the periodic and the aperiodic signal. Why this is so? If you see the first line, your answer lies over here. a non-periodic signal may be assumed as a limiting case of a periodic signal. Okay. So you are defining over here itself that your aperiodic signal, they are basically constituted of the periodic signal. Okay. So if you are able to analyze non-periodic signal, then you should always also be able to, because that is a limiting case of the periodic signal. If you are able to analyze the limiting case of a periodic signal, limiting case of a periodic signal, then you should also be able to analyze the periodic signal itself, right? So why this is so? If you see, suppose we have a signal component. There's something like this. It goes up to infinity. It happens over here. Then what it says, then at this infinite level, it would again start something, the same thing, and it would again go up to infinity. Again it would rise, and again it would be like this. So in say infinity, 2 infinity, 3 infinity, like this. So you are telling your aperiodic signals, they are also periodic signals, but their time period t, it is tending to infinity. Now you see the sinusoidal signals, the basic periodic signal, it go like this, right? So if you take the infinity point, over there also it is periodic. If you take a smaller point, a smaller time duration, then also it is periodic in nature. So your Fourier transform, it is capable to handle both periodic and aperiodic signals. So that's why if you see herein, we have started the derivation using the Fourier series component itself. Okay, and as we do some derivation, we come to this point where we have the forward transform, which is basically the Fourier transform, and we also have the inverse Fourier transform. Okay. Now if you see the operator over here, it is integral operator. So that means the Fourier transform, it is able to handle infinite number of sinusoidal signals. Okay. Again, if you see, to get to the frequency domain characteristics, we need xt multiplied by a complex exponential signal, and also in the inverse Fourier transform, we multiply the frequency domain signal with a complex exponential signal. The complex exponential signals, they vary, of course. They are called the this exponential operators. So they are varying. That's a separate thing. But the essential is that both of them are being multiplied and then integrated over a period of time with a what you call complex exponential signal. Okay. So what is happening? You have a signal. You apply the Fourier transform. You get to the frequency domain signal. Again, from here you come over here, you apply the inverse Fourier transform, and after applying the inverse Fourier transform, you get this thing. Okay? And this is the most important transform in the history of the mankind. Whether you say medicine, whether you say geology, whether you say physics, whether you say mechanical engineering, wherever you want to go, you will find that Fourier transform, it plays a significant role in the analysis of the signals. Okay, and this is the important thing, and this is what it makes it so versatile in nature. However, it has got some disadvantages which we will be discussing at a later stage. Okay, so many students, they don't know how a frequency domain signal and how a time domain signal it looks like. For them, I'm just uh, drawing the two types of signals. So in the time domain signal, you will be having the amplitude and the time. and your signal component will vary like this. When you perform the Fourier transform, here the independent operator is omega, that is the frequency. Either you can put it in omega or f. Okay, and again amplitude. Now, herein you are finding out what are the frequency components which are present. So here, suppose you have a square wave which is having a frequency, or any signal having frequency component, say 50, 100, then say 125, say 200, and so on. Okay, so let us consider that we are having this four frequency component in a signal. So what we will get is that we will get peaks, let's say 50, 100, 125, and 200. So your peaks, after you perform the Fourier transform, you will get a signal something like this. Okay, so wherever is your frequency component which are present, which are the constituting frequency of your signal, at those location you will be getting the peaks. Okay, so this is a non-periodic signal, and the second is the periodic signal formed by the periodic extension of the xt. Then relationship between the inputs and the outputs in an LTI system. So it looks somewhat clumsy, so I will initially draw it in a simplistic manner. Say you are having an xt, and we have hd. This hd, if you see this hd, it is regarded as the impulse response of the system. Okay, impulse response of the system. Suppose in a class there would be a, say, one of the calmest boy or a girl, and there would be a very aggressive nature of a guy or a girl, right? So if you stimulate, if you irritate the guy who is calm, he may get irritated momentarily, and then he will come down very pretty quickly and he will get calm. Okay, whereas the person or your friend who is not that calm, and if you irritate him, he will be irritated for a longer period of time, right? He will be irritated for a longer period of time. So what you have done by irritating him, what you do is, we call it, don't irritate me, or what do you call, don't ping the guy. Okay, so what we are doing, basically we are giving an input signal for a very small time, and we are irritating the person. So that is the impulse input. Okay, that is the impulse input, and that is nothing but our delta t. Delta t, what we are seeing, it is having amplitude at t equals to 0, and or at all other frequencies it is not having anything. So whatever the response you get after you give the input impulse, it is regarded as impulse response. So this ht, it is nothing but the output of the system yt, when you have given an input impulse to it. Okay, delta t. So we can say that when we give delta t as the input, we will get ht, and this ht, it is the characteristics of that person. In this case it is the system. Okay, so by pinging a person, you will be able to understand the nature of the person. Here also, by pinging the system, you are able to understand the characteristics of the system. Okay, so that's why it is called impulse input, and this is impulse response. Input and response. Okay, Now, once you know the characteristics of the system, then what is yt? Yt is given by xt convolution of h of t. Okay. Now, what happens in the frequency domain? Convolution is a very complex procedure. Okay. So we will be covering it at a later stage. So let us understand. When we have the So the question arises, can we perform the numericals in a simplistic way? Yes, there is a possibility. But what is the possibility? The possibility is that suppose you are having this xt, you perform Fourier transform, we get to the x omega. Similarly, we have ht over here, we apply Fourier transform, we get h of omega. Okay. Then the output y of omega, it is given by x omega multiplied by h omega. And believe me, doing multiplication, it is easier as compared to doing the convolution. Okay. Now, once you got this output, you perform inverse Fourier transform and you get the output of the system. Okay. So, this is basically the input-output relationship of an LTI system, and how the Fourier transform, it can help us in analyzing the system. Now, coming to the Fourier analysis of the discrete time signals. So discrete time signals, as I already told you. So first one is the Fourier series representation. So basically it is a Fourier series, but in the discrete domain. Uh, so xn equals to x of n plus capital N. You can see over there. So this is the equation of the Fourier series. Okay. Again, a complex exponential signals, they are being used to represent the periodic signal. Okay. Now discrete time Fourier transform. So what happens? I am directly going over here also. If you see, we are starting with the same discrete time Fourier series, and then we are synthesizing, or we are deriving the equations for the discrete time Fourier transform and inverse discrete time Fourier transform. So can you tell me, from these two equations, is there any disadvantage of this system, of this transform? Sorry, is there any disadvantage of this transform? Anyone? थोड़ा दिमाग लगाओ. I have already told you in between. हाँ हाँ. क्या है? लिमिट. काइंड ऑफ. मान लो मैंने उसका ये कर दिया, एन एन कर दिया, कैपिटल एन कर दिया, से फॉर एग्जांपल. नो. हाँ हाँ. कहाँ पे? X of n, it is equal to 1 by 2 pi. Then we have an integral operator. नहीं, इसको तो हमने ये कर दिया ना, कैपिटल एन वी कंसिडर्ड. So the problem lies in the inverse discrete time Fourier transform. Here we have an integral operator. Integral operator cannot be implemented in the digital systems. Okay, then you have to do infinite number of calculations. Summations, they are discrete operators. Okay, so forward transform you can do it, but inverse transform, the digital systems, they will not be able to handle it because we have an integral operator. So that is the problem with the discrete time Fourier transform. So yeah, we have still have time. So these are the discrete time things. The same thing what I told you, delta n, it is nothing but your impulse input. Hn It is nothing but the output of the system when you give the impulse input as the input. Then you have the x of n, you can get x of omega, then h of omega is there, it is already there, then y of omega, it is given by x of omega multiplied by h of omega. The same thing. Okay. So herein, if you want to do it in the frequency in the time domain, it has to be a the this convolution operator, and in the frequency domain, it is the multiplication operator. Okay. So due to this disadvantage of the discrete time Fourier transform, we needed to have another transform where this integral operator could be eliminated, and this is the reason why we had discrete Fourier transform. This is the reason why we had, or there was a need for another transform like discrete Fourier transform. So I'm not going into the all of this. I will just go to the this chart over here, and this is a very good chart. Okay, so which tells us what is happening in discrete Fourier transform. Okay, so the source of this chart is the Pinterest. Okay, so initially I found it somewhere this graph, but somehow I lost the track. Yesterday I could again relocate it by just Google searching the image. So I was able to find out, and it showed that it is Pinterest, but I still don't know whether it is the original source or not. But yeah, due credit to the Pinterest. So this is a very good chart. What we are doing, okay? So initially, if you remember, when we are sampling the signal in the time domain, I said you we band limit the signal. Okay. Suppose if my sampling frequency for the signal is Fs, then Fs should be greater than equal to 2 of Fm. Okay. So Fm is the band limited signal. Fm is the band limited signal. Okay. So for frequency for time domain sampling, we are doing band limiting in the frequency domain. Okay. Keep this in mind. It will be needed. So if you see this portion initially, so we have the time domain signal over here. Then for sampling, I told you we have to multiply it with the impulse train. So we are multiplying, we are getting a time limited signal. Sorry, the sample signal, not time limited. Sorry. Are you getting my point? Now, for this, what we had done, we had band limited the signal in the frequency domain. Now, if you see the frequency domain signals corresponding, so it should look like this. It looks like this over here. Then we are, if you do the Fourier transform of this sample signal, what is happening? If you see, we are having frequency component say minus fm to plus fm, say for example, and up to 2 fm it was having nothing. Now, if you see over here, what is happening at these locations, it should have stopped. Okay. However, beyond this, we can see the repetition of this frequency components. Repetition of the frequency components. That means when we are sampling any signal in the time domain, it starts getting repeating itself in the frequency domain. Okay. I would give you a simple example. Suppose this is the bandwidth Fm minus of Fm. This is Fm. Then we are having minus of 2 Fm then we are having 2 of Fn. After you sample it, after you sample it, this frequency component, they start repeating itself. Now, if you see from here to here, we are going from low frequency component to high frequency component. Again, when it is repeating, it should be see from low frequency component to the high frequency component. That means at this juncture, just prior to the FM, we are having high frequency component, and just after the FM, we are having low frequency component. Okay. If proper care is not taken, if this Nyquist criteria, this is called, this equation, it is called the Nyquist criteria. If this is not followed, then what happens? This low frequency component, it gets mixed up with the high frequency component, and there will be overlapping of the signal components, and that would lead to a condition with, that is regarded as the aliasing. Aliasing. Okay. Now, what does this do? When aliasing happens, when your high frequency component gets mixed up with the low frequency component, the nature of the curve totally changes. Whatever is your original curve, it would look like, its nature would change. Okay. If the aliasing, what is happening, is due to the condition wherein you're using an analog to digital converter, right? So the components that are being used, they will always be non-idealistic in nature, and if they are non-idealistic in nature, that would also lead to some mixing of the, might lead to, not always lead to, might lead to some frequency mixing of the low frequency, high frequency component and the low frequency component. So that condition, it is called, even though it is aliasing is happening, that is called frequency leaking. Okay, that is called leaking, because that is due to the non-idealistic parameter of your hardware. But if you do not follow this condition, then it is aliasing. Okay, though both are same, but technically they are different. One is you are not following the principle, another is you are following the principle, but due to the non-idealistic nature of your device, you are getting this problem. So one is aliasing, another is the this frequency leaking or frequency leakage. Okay. So herein, this is one of the important thing to see. So when we have sampled our frequency component, they are getting repeated itself. Now, the thing is that if we want to change this thing to a summation operator, what we need to do? This is in the frequency domain, right? We are doing the operation in the frequency domain. That means we need to sample the, whatever the frequency domain, this thing we have got, signal we have got, we have to do the sampling of that. However, I told you, when we are sampling, we did the band limitation in the frequency domain. Similarly, when we want to do this, what do you call, sampling in the frequency domain, we need to time limit the signal. We need to time limit the signal. Okay, that means within a specific time, we need to restrict our signal component. Okay, so if you see, now once you get this sample signal, what we are doing, we are taking this part. Okay, so we are time limiting the signal with a rectangular, what do you call, time domain operator, and we are just multiplying it, not the operator, time domain filter you can say. So we are just cutting a piece of the signal from there, okay, creating a window in the time domain, okay. So once we do that, we have time limited the signal, and if you see the signal, it's still is repeating itself. Now the next thing is, after so much of the processing being done in the time domain, we now need to go to the frequency domain. Now if you see over here, after we have time limited it, we have got this signal. Now we are multiplying it with an impulse train in the frequency domain. In the frequency domain, okay. So once you do that, you see you are getting a sampled frequency domain signal. However, if you look over here, your time limited signal, it is also getting repeated itself. After this period, minus of t by 2 to t by 2, from here minus of t by 2 to t by 2, the signal is repeating itself. And that is why if you do not time limit the signal over here, what will happen? These signal components will be getting mixed up with the original signal components, and you will be having the trouble in analyzing. This is bit complicated, but try to understand the what is the mechanics, what is going on. Otherwise, if you go to the mathematics, you will be totally lost. So that's why I am telling you, just have a clear picture what is happening in the discrete Fourier transform, and this will be the base for you, or the fundamental for you, for entering into the digital signal processing. Okay, so this is what our discrete Fourier transform does, or we have to do the discrete Fourier transform, so that we can what do you call, analyze a signal in the digital hardware. So we have to band limit, we have to time limit, we have to sample the signal in the time domain, we have to sample the signal in the frequency domain also. Okay, so mm, this is the gist of the discrete Fourier transform. So this is the equation of the discrete Fourier transform. So we have x of k, which where herein the k is your frequency domain here. So we are going into the frequency domain. So we are having xn multiplied by w k n by n, and this is called the DFT, where k value it changes for yeah, 0 to n minus 1. Also the n value, if you see, it changes from 0 to n minus 1. Similarly, IDFT, if you want to go back to the original signal, the same triple factor operator would be there. However, there would be a minus sign. And what is this triple factor operator? This triple factor operator is given by Wn, it is power minus j 2 pi divided by capital N. And so if you have this kn over here, basically it is basically minus j 2 pi small kn divided by n. Okay. So all this j 2 pi kn, it is in the numerator. Okay. It is power minus j 2 pi kn by capital N. Okay. तो इसका e का ये होगा. So this factor, except the kn, it is regarded as the total factor matrix, total factor. And tomorrow we will start with what is the importance of total factor. And from there we will take it up. Yeah, already it's 9:55, so there is no scope of anything. Mm-hmm. कौन सा? Gibbs phenomenon. See what we are saying. We are trying to recreate this signal by adding up infinite number of sinusoidal signals. Okay. However, when we are practically doing it, we are using only n. N means say maximum 100 signals. Because digital signal systems, they cannot go take infinite number of sinusoids. If it is a very good processor, you can go up to say 1000, right? But it is still not infinity. So what would happen to the perfection? There will be somewhere that imperfection will come in. So if I give you a task, you do this task, you'll be doing on your own way. Okay. Then if I ask, okay, you make a group of say 5 people, you do the task. Your perfection would be somewhat better. Then I say you do the thing and include all the persons in the class. Your perfection will still improve. Okay. Then think of the stuff if you can do the same work where you are engulfing thousands of the people and you are improving it, your perfection will again increase. Okay, but it may not be totally perfect. So this is what it is saying, that when we are talking about any signal, we are considering that signal is made up of infinite number of sinusoidal signals. However, we are recreating here the same signal but using an n number of signal, which is quantifiable. So due to this quantifiable, somewhere the imperfection should come. The imperfections come in the Bessel levels and this amplitude levels. So where there would be some ripples. These sinusoidal things, small spikes, they are called ripples. RIPPLES. Okay. However, these ripples, they get more pronounced at the discontinuities. That means where from 0 to the maximum the value is going at those locations, say at not only in the upper side, in the lower side also, you see there is a slightly increased change in the amplitude levels. So this phenomenon, it is regarded as Gibbs phenomenon.